Analytical Chemistry 1, Lesson 24. Solving chemical equilibrium problems involves solving a set of simultaneous equations. We know that there is always a charge balance equation, and there is one or more mass balance equations. The other equations that are required are the various chemical equilibria involved. Their equilibrium constants need to be known or be found. If you do not have a table that gives you a particular value for K at the temperature you need, you can always use thermodynamic formation data, delta G naught of formation, to find a delta G naught for the reaction, which can then be used to find K. But in some fashion, if the equilibrium problem is to be solved, you need all this information. It is worth reminding you at this point that if you were to use activity coefficients, they would appear in the equilibrium expressions, but they would not appear in the mass and charge balance expressions. The activity expresses a species' chemical behavior, its apparent concentration. The balance expressions have to use the actual concentrations. So you count the number of equations you have and the number of unknown concentrations that you need to find. You must have as many equations as there are unknowns, otherwise the problem is underdetermined. And you will also need to use some chemical insight. And while the complete solution of even the most complex equilibrium situation can be solved, we often make approximations using our chemical insight to hasten and simplify the solution. Let's look at some problems. What is the pH of an aqueous solution that is 1 millimolar in HCl? There are two reaction equations to consider. Whenever water is the solvent, there will always be the autoionization of water, and we also need to consider the dissociation of the HCl. The charge balance equation reminds us that there will be protons arising from both water ionization and HCl dissociation. The mass balance is best cast in terms of the chloride ion. The analytical concentration is 1 millimolar, and it will be partitioned amongst the chloride ions and any residual HCl molecules. Each equation has an equilibrium expression. That for water has its equilibrium constant as 1 times 10 to the minus 14. A more precise value at 25 Celsius is 1.007 times 10 to the minus 14. And what about HCl? Well, here's where we start to apply some chemical intuition. HCl is a strong acid. It essentially fully dissociates in water. Its equilibrium constant is very large. Its experimental measurement is very difficult, but theoretical calculations put it around 10,000. But in essence, there will not be any undissociated HCl to speak of. So we make the approximation that the concentration of HCl is 0, and from there, simplify the mass balance equation. That leaves us with 3 equations and 3 unknowns. HCl is no longer unknown. Our chemical knowledge assigned it to 0. The strategy one follows is to reorganize one equation to solve for one unknown and then substitute it into another equation. You continue to do this until you have an equation you can solve. We are asked about pH, so let's aim to have an equation with only the concentration of H plus in it. Rewrite the water equilibrium to solve for OH minus and substitute that into the charge balance. Our very simple mass balance equation has also given us the equilibrium concentration for chloride ion, 1 millimolar. Reorganize the equation and you will see that it is just a standard quadratic equation. Watch the signs. Both the HCl concentration and Kw terms are subtracted in this expression. Use the well-known quadratic formula and find the hydronium ion concentration to be 1 millimolar. Hence the solution pH is just 3. Now this is not likely a surprising answer for you. Your chemical intuition probably told you right away that with a strong acid, the H plus concentration is just the formal concentration of the acid. If you look at the quadratic formula expression, you see immediately why this is the case. The second term under the square root symbol was the contribution from the autodissociation of water. It is about 8 orders of magnitude smaller than the contribution from the HCl. An answer to 3 significant digits explains our result. Here's another one. What is the pH of an aqueous solution that is 10 nanomolar in HCl? So the same question, just with a smaller acid concentration. You might recognize this as a common trick question. Given the last result, you might be tempted to conclude that since HCl concentration is 1 times 10 to the minus 8 molar, then this would be the H plus concentration so that the pH is 8. But think about it. We have pure water at a pH of 7. We add, admittedly, a small amount of acid, but we do add some acid nonetheless. And then we declare the pH to be a comparatively basic 8. We would expect instead the solution to be slightly more acidic than pH 7. So let's do the work. The equations are the same. The only difference is the magnitude of the formal HCl concentration and thence the chloride ion concentration. We arrive at the same quadratic and solve it in the same way. This time the concentration is slightly greater than that found in pure water. The pH equals 6.98, just slightly more acidic than pure water. Lesson to be learned is that we have to watch the shortcuts that have been taught, make sure we understand their limitations and when we are able to employ them and when a more rigorous solution is required. Another problem. What is the pH of an aqueous solution that is 1 millimolar in cyanoacetic acid, NaCH2COOH? Now this is a weak acid, so we expect that it will only partially dissociate. The equilibria are given here. Now I'll use AC for acetate just to simplify our notation. Here are the charge and mass balance equations, and we have 2 equilibria we need to consider. Counting, we have 4 independent equations and 4 unknown concentrations, so the problem can be solved. But hold on as I go through the solution. There are a few mathematical steps. Don't get lost, but I want to show that it really can be solved completely. Now stop the video at each stage to make sure that you get the algebraic manipulations. Start just like before. Rewrite the water equilibrium, solve for OH, substitute into the charge balance equation. Now we are going to go looking for another expression for the cyanoacetate concentration. Rewrite the acid equilibrium, solve for the cyanoacetic acid concentration, substitute it into the mass balance. Gather the terms in cyanoacetate and solve for cyanoacetate. Substitute this back into the charge balance equation to eliminate the cyanoacetate term. Now this is an equation that only has hydronium ion concentration as a variable, and the rest are known constants. We now have to expand this equation in H+. Multiply the 2 denominators in sequence to get rid of them. Now again, pause the video to make sure you can follow what I've done. Expand the terms in brackets and then gather the like powers of H+. And again, pause the video to make sure you can follow along. Give the highest cubic term a 1 as a coefficient by multiplying through by Ka. Here we have a cubic equation in hydronium ion concentration. Our task is to find a value for H+ that satisfies this equality. Now mathematically, we're just asking to find the roots of this polynomial in H+. There are formulas that can be used to solve a cubic, just like there is for a quadratic. You should look it up on Wikipedia just for fun. There are 3 roots. In some cases, you get 3 real roots and would have to choose the one that made sense. In other cases, you would get 1 real root and 2 complex roots. Only the real root makes sense for the problem. In any case, there is always a real, sensible solution. More complex chemical equilibria can lead to even higher order polynomial equations. There are equations to solve for quartic equations, those of 4th order, but there are no known solutions, what we could call closed form solutions, or a set of equations that can give the solution for 5th order or higher. There are, however, numerical solutions that can be very effective. The first is brute force. With a computer, just because a calculator would be very tedious and prone to errors, by using a spreadsheet such as Excel, choose a cell to the H+ concentration you want to test. In a neighboring cell, write out the cubic equation using the first cell for the hydronium ion concentration. You'll need to use other cells for the constants you need to use. The strategy is to enter different values for H+ in the cell, which then calculates this polynomial equation. When you approach the right value, the calculation will get closer and closer to 0. The equation produces the required equality. Your chemical insight will give you a head start on the expected range in which you will find the correct H+. Enter your first guess. Note the calculated result. Change your guess a bit. Is the new calculated result closer to 0 or farther away than the first one? If closer, change it again in the same direction. If further away, change it in the opposite direction. Continue this process until you converge on a result where your proposed H+ concentration has enough significant figures that are not changing from one guess to the next, and the result is close enough to 0. There are ways to automate this, but there are also challenges with the process potentially diverging to plus or minus infinity, or oscillating around some result, or converging very slowly. Mathematicians and computational scientists have developed considerably more intelligent approaches to finding the roots of polynomials, which is the problem we face here in mathematical terms. One of the oldest is known as Newton-Raphson. Yes, that is Sir Isaac Newton. He used calculus to guide each subsequent guess to converge on the result more quickly. Other approaches have improved on it. The Jenkins-Traub algorithm is a very effective approach. Now, both of these are interesting strategies for root finding. If you have a background in programming, you might find it to be an interesting challenge to look up the equations and try to implement them. Being able to quickly solve chemical equilibria problems has been a great boon to chemical industry. It is widely used in solving problems with reactor designs. The mining and purification of lithium was tremendously advanced by finding the right chemistry mathematically by studying many different equilibria. Once the best chemistry was identified mathematically, lithium production increased an order of magnitude and today makes things like lithium batteries affordable. But for you, what approach can work for you? The brute force method can work, but you have to be careful, knowledgeable, and it takes time. Excel has another tool that can be helpful. It is called GoalSeek. Under the Tools menu tab, you will find it listed. It is a way to automate the brute force technique. You still need the cell for H plus concentration and another cell that calculates the cubic or higher equation. When you select GoalSeek, you simply give it the addresses for these two cells along with the goal you want to seek, which is 0 in our case. You can watch it change the estimate for the H plus concentration and observe as the result gets closer and closer to 0, and then stop when it gets close enough and the value in the H plus cell is the answer to your problem. There are things that have to be set correctly, and there are other potential problems one needs to be aware of and find workarounds, but the tool is actually very useful. You will use this most commonly throughout this course. Now we'll discuss this some more, but to mention a couple of things you need to do, go into your application preferences under Calculation. Make sure Use Iterative Calculation is selected. You likely will not need to change maximum iterations from its default value of 100, but if you run into a situation that is converging very slowly, you can increase this number by a lot. You do need to change the default value for maximum change. Once the difference for the calculation from one iteration to the next goes below this value, the process stops. It usually defaults with a value of 0.001, but for your work you will need to make it much smaller, 10 to the minus 12, 10 to the minus 16, even 10 to the minus 23. You will see when you have enough resolution for your results. Excel has another tool that is more sophisticated called Solver. In some versions it is an add-in to the program. Go to Tools and select Excel Add-ins, add in the Solver. Now Solver should appear in the Tools menu. Solver is set up much like GoalSeek, except it can handle the adjustment of several cells simultaneously. Not usually a need for us, but it's good to know that it exists. Other commercial packages have even more robust routines. If you have MATLAB, for instance, the function roots takes a vector that is the coefficients of the polynomial and gives back all of the roots, real and complex. You can then view them all and choose the root which makes sense. It will always have one root that makes chemical sense. That means it's going to be not complex, it's not going to be a negative real, the concentration that it suggests will not be so large as to not make sense, things like that. And Maple can do the same thing with its function solve. So what is the solution to our problem? Using Excel's solver, we get the result that H plus equals 8.07 times 10 to the minus 4 molar. So that means the pH of the solution is 3.093. If you use MATLAB, for instance, you get all three roots. But the other two are negative, and a negative concentration makes no sense. So we know to choose this root. What about the concentrations of the other species? Armed with this new value for H+, go back to the original four equations. First, use the water equilibrium to solve for the hydroxide concentration. So it's very low at about 1.25 times 10 to the minus 11 molar. And that's just what we would expect for an acidic solution. Now use the charge balance equation to solve for the cyanoacetate concentration. Interesting. Because OH is so small, the H plus and cyanoacetate concentrations are essentially identical. Now you can use either the weak acid equilibrium expression or the mass balance equation to find the concentration of undissociated acid. Both equations give the same result. The undissociated acid has a concentration of 1.93 times 10 to the minus 4 molar. The equilibrium problem has been completely solved. This approach can be used for any monoprotic weak acid. Just change the formal concentration and the acid equilibrium constant. And remember that we found that H plus and acetate concentrations were the same. This will be the basis for our approximations that we will come back to in the near future. What if we are dealing with a monoprotic base rather than a monoprotic acid? How does that change things? Well, the reaction equation is now the base hydrolysis expression, and the charge balance sums the protonated base and the hydronium ion together to equal the hydroxide ion concentration. The base hydrolysis equilibrium expression has the appropriate corresponding form, and the mass balance is similarly formed. The four equations to solve have the same form as in the acid case. If you work through them, you will see that you do indeed arrive at the same cubic polynomial, except that OH minus replaces H plus and Kb replaces Ka. Consider a 1 millimolar solution of piperidine. Its Kb is 1.34 times 10 to the minus 3. Using solver or any of the other math tools, we get that OH minus equals 6.675 times 10 to the minus 4. This corresponds to POH equal to 3.176. If we are asked to provide the solution pH, then from the water autodissociation reaction and using Kw equals 1.007 times 10 to the minus 14, we get that the pH is equal to 10.821. This is a nicely basic solution that would be expected from a weak base with such a comparatively large hydrolysis constant. We can substitute into the original equations to obtain the concentrations of the other species. Note how the protonated base has the same concentration as the hydroxide ion. This arises for the same reason that the acetate and the hydronium ion concentration were the same in the acid case. And, remember this for the future, it will solve a lot of problems for us.